Hello everyone. This video will discuss limits and continuities. So the following are the topics that we will discuss for this video. So we have the introduction, the concept of limit. So we will know why there is a need to study limit, and we will a little bit tackle graphical and numerical methods to estimate limits, though we'll not go through the in-depth of this because uh, these are only estimation and these are prone to errors. The third is the very important part of this video, the properties of limits, and then the fourth, the vertical asymptotes, the fifth, horizontal asymptotes, sixth and seventh, continuities and discontinuities, respectively. So we'll now go first to the concept of limit. We need to discuss why there is a need to study limits. So you already know. Imagine yourself, no, na you need an item of a certain kind that you go looking for it in the appropriate store, and you discover that the store has all kinds of other items that are similar to what you need but not exactly the item you want. For example, gusto ka mo palit og toothpaste. You want that toothpaste nga kana nga brand imong gusto, pero wala na sa departments, wala na sa supermarket mo nakita. So the sentiment you have had in choosing the brand of toothpaste is just like the same of the limit. In the world of calculus, there is the situation when we realize that we need a limit. We need to compute a certain quantity through a formula that we may know, but that formula does not work exactly for the numerical value we need. So limit was developed. Limit was developed to quantify the numerical value of a formula, even though the formula does not work exactly for the numerical value we need. And also, the motivation of developing a limit was that of computing the slope of a line of a tangent to a curve at a given point. So let us consider this graph, no? Yeah. So we have this definition, the slope of the line joining two points P and Q. So this is your P. I'm sorry. So this is your P and this is your Q. Now, these 2 points are points within the graph. So the P, this is the coordinates of P. Let us say this is from the origin. This is X. Okay, so the difference between P and Q with respect to the x-axis, we say this is H. Okay, and of course we know that in the notation of function, when you substitute x to a certain equation, that will evaluate the equation, and that your dependent variable will become the function of your independent variable, such that when you evaluate x, that will be your this one, the value of your dependent variable here. This is your f of x, and same with q. This is your f of x, because this is x plus h, so x plus h. So basically, your q has these coordinates, x plus h, this one on the x-axis, and y-axis the f of x plus h. And of course, your p has these coordinates, x and f of x. You know, in algebra, the slope is equal to rise over run, and your rise is if you will draw a triangle here, just yeah, this one, it's a right triangle. You know that this is a curve, but for a very very small distance between P and Q, you can say that this is close to a straight line. And if that is close to a straight line, then we can say that it is very near to a right triangle. So taking note of a right triangle, yeah, para klaro, no? Okay. So this is a right triangle. We know that rise over run, that is your slope of the line, PQ. Then that would be the y minus 2 minus minus y sub 1 all over x minus 2, or x sub 2 minus x sub 1. I'll repeat, the m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This is what you learned. This is what you have learned in the algebra. And this is equal to, we know that y sub 2 here, this is f of x plus h minus y sub 1 is f of x plus h minus f of x. No, this is y sub 2, this one is y sub 2, this is one is y sub 1. Correspondingly, this is x sub 1 and x sub 2. So your y sub 2 is f of x plus h minus f of x over the difference of x, which is x plus h minus x, and x minus x is 0, so we have the remaining h. So this will yield to this equation. So your slope now is equal to f of x plus h minus f of x all over h. And take note, this is based on the assumption that your h is a very very small value. So we denote that h is an arbitrary real number that for whatever reason it is, that is a very small, very infinitesimal value. To say that a quantity q, be it independent or dependent, approaches to a certain value c, means that we can make q arbitrarily close to c, such that q is approaching c. So this is the notation that we are always using. Q approaches c. So this notation arrow means approaching, that is approaching c. So this one, notation arrow, that is approaching c. Okay, so much for the notations and definition. We have another definition. The problem of finding a limit of a function, the problem of finding the limit of a function y is equal to f of x when x approaches c refers to the problem of determining whether f of x approaches some value as x approaches c, regardless whether f of c exists or not. So unsa may gipasabot ani, no? Let us try to have this one, no? Let us say you have this graph. So you have the you have this graph. No. Let's say this is y is equal to f of x. Okay. Now for a certain value here, let us say for a certain value c, then not as positive. For a certain value c, let us say here, for certain value c, you want to know at what value will the graph approach to when your x approaches c. So meaning, at what value will your graph approach to if your domain, or if your independent variable, the value of your independent variable approaches c. So it is not the finding the limit, it's just finding the value that the graph approaches to after the independent variable, the value of your independent variable approaches that certain value. Let us say, for example, no, this one. Let us say the c at this value approaches 1, no? So the value of your function y is equal to f of x, or the value of your function y is equal to f of x as x approaches c is equal to 1. Later we will learn, no? We will learn later the how will what is the correct notation for this definition. So another definition, if as x approaches c, f of x approaches negative or even becomes identically equal to a finite number L, we say that such number L is the limit of f of x as x approaches c, and we write this as a limit of f of x as x approaches c is equal to L. So the graph, this graph, sorry, so this graph, we have this graph, this one. If you have there the c, this is the point of concern, this one. This one is the point of concern. Now, we need to find the value of the limit as x approaches c. So it is not the point c itself, but the boundary, the approaches of your point c. So this one and this one. At that point, there is what we call the value correspondingly to your dependent variable, and that would be the range of that would be your limit. So if no such number L exists, we say that the limit does not exist, and write this limit f of x is equal to dne, or you just say the limit does not exist. Okay, to fully understand the theory of limit, with basing on the definition that we have had, let us try this example. No, evaluate 1 limit of x squared minus 2x plus 3 as x approaches to 2. So we'll try to evaluate limit of x squared plus 2 minus 2x plus 3 as x approaches to 2. So okay, I just have to remind you, no, ganito kayo dapat mag-solve. Let me just check if makita ba yung whiteboard. Okay, kita nga. Okay, so limit of x squared minus 2x plus 3 as x approaches to 2. So by direct substitution, as x approaches to 2, the limit of this function becomes limit of the limit of this function becomes, you just substitute the value of x, 2, so that is 2 squared minus 2 times 2 plus 3, that is equal to 4 minus 4 plus 3, that is equal to 3. So therefore, this is the notation of therefore in the algebra. Therefore, the limit of x squared minus 2x plus 3 as x approaches to 2 is equal to 3. Now, my question is, what is the meaning of this value here, 3? So, if you want to graph that one, x squared minus 2x f of x is equal to x squared plus, is that 2 plus this minus 2x plus 3. So this is a parabola with a vertex at 1 and 3. If this is we will denote this one as y is equal to, this is our dependent variable, x squared minus 2x, and then complete the square. Half of negative 2 is negative 1. Negative 1 squared, that is positive 1. So this is a perfect square. Now this one, to complete 3, you add plus 2. So nothing has changed with the equation. So x minus 1 quantity squared is equal to, you just have to transpose 2 to the right, to the left, I mean, y minus 2. So therefore the vertex is at 1 and 2. So this is the vertex. Yeah, these are all learned in algebra. So we'll have to generate coordinates of this function x squared minus 2x plus 3. So we'll start, we will have one vertex 1 and 2 as our benchmark points, and I'll just have at least 5 points including 1. So 1, 2, 0 and negative 1, 1, 2 and 3. And this is x, this is y. Oh no, and that should, yeah, okay. So if x is negative 1, of course negative 1 squared is positive 1 plus 2 plus 3, that is equal to 6. If x is 0, of course this is 3. If x is 2, 4, 4, still 3. And if x is 3, your y or your f of x is, this is just in notation in algebra, this is also considered to be f of x. They are just equal. So when x is 3, 9 minus 6 plus 3, that is 6. Let me just check kung makita ba yung 6. Okay, kita nga. Okay, so we have now the coordinates. I'll just have to graph this one for the benefit of the many, so that I can properly explain what is the meaning of this limit. So if I have to graph that one, sa itong pinakadako, sorry, negative 1 to 3 for x, 1, 1, 2, 3. For y, you have 6, 1, 2, 3. Just have to redraw again a graph. Okay, so negative 1, 1, 2, 3, and then 1, 2, ang laki ng one, 2, 3, 4, 5, 6. Okay, so this is 2, 4, 6 na nag-concert sa Picas. And this is negative 1, this is 2, 1, 2, 3. So our first coordinate is negative 1, 6, negative 1, 6, this one. Our second coordinate is 0, 3, 0, 3. Our third coordinate 1, 2, 1, and then 2. The fourth coordinate 2, 3, 2, and 3. And fifth coordinate 3, 6. So by these 5 points we can draw our parabola, a second degree curve. Okay, so this one is f of x is equal to x squared minus 2x plus 3. So this is our parabola. Now, the limit, according to the limit, what happens to x squared minus 2x plus 3 as x approaches to 2? So that is the basic definition of a limit. So if we want to analyze it by the graph, what happens to the graph, or what happens to the function x squared minus 2x plus 3 as x approaches to 2? So as x approaches this one, this point here, okay, as x approaches that point, your graph also approaches what? This part here, and that is what? That is 3. So that is why the limit of x squared minus 2x plus 3 is equal to 3. Okay? So that is the definition of a limit, and the function of a limit unsa iyahang gamit, no, sa differential calculus. So later on we will be able to fully appreciate the uses, or the use of a limit when it comes to undefined functions. Okay, so next we will now define, we will now evaluate limit of 1 over x as x approaches 0. So we will try to answer this. I will not try, we will answer this one. It is our obligation to answer this problem. Okay, so number 2, limit of 1 over x as x approaches to 0. Excuse me. By algebra, 1 over x is equal to an undefined value. But in calculus, 1 over 0, or any number, let us say a over a value 0, that is an undefined value, or undefined function, undefined number. But in the calculus, when we say 1 over 0, that is close to approaching a very, very large number. You try dividing, let's just say 1 divided by 0.0001, you will yield a relatively large number. Such that 1 over 0 in calculus is a very large number, that is infinity. Okay, so when you evaluate this limit 1 over x as x approaches 0 by direct substitution, so let's just abbreviate that one, BDE, by direct substitution. Limit of 1 over x as x approaches 0 is equal to 1 over x is equal to 1 over 0, and that is equal to infinity. So therefore, just have to erase this one, may nagko-concert pa sa kabila. So limit of 1 over x as x approaches to 0, therefore limit of 1 over x as x approaches 0 is equal to infinity. So this is your answer. Now if you want to try it graphically, you can, no? You just have to you will always yield to something that will satisfy your curiosity, whether is it really possible that the limit of 1 over x as x approaches 0 is equal to infinity. Yes, if you want to graph that one, you can. Let us just try to, for the benefit of your curiosity. We say this f of x is equal to 1 of x. So we'll have to generate again values. Let us say the values 0.2 until it approaches nearly 0. Let us say from 1 to 0, x, f of x. I will start from sorry. Okay, so we'll just I'll just have to start from 1, 0.5, let's say. Let's say 0.1, 0.01, 0.001, and 0.0001. Relatively large. When x is equal to 1, your f of x is 1. When x is equal to 0.5, your f of x is equal to 2. When x is equal to 0.1, that is relatively large, that becomes 10, right? For this is 100, 1000, 10,000. So if you want to graph that one, just wait. Okay, so if you want to graph that one, wala po. Okay. Let us say this is 1. This is 0.5, 0.25, 0.125. Okay. And this is 100, 200, 300, 400, 500, 600, 700, so on and so forth. When we say 1, this is 1. This is 100, 200 ni, 400, 600. So if this is 1, and your f of x is also 1, gamay kayong 1, no? Dara. So, magamit ko line color para mas makita siya. 0.5, mo ni 0.5 nimo, 2. So, gamay gapon. Gamay kayo in compare nimo sa 100 ni unit. So, nagapon sa diri. 0.1, this is 0.5, 0.125, another siguro ang 0.1, and that is 10. So, 1/10. No? And then, 0.001, gamay na kayo, niabot na siya 1,000. Up to 0.001, 10,000. So, kung imo nang i-graph, inani mo hang now, you try x is equal to 2. Ang magawa sa iya is 0.5. So, mugamay siya maayo dari mo taas siya og maayo. So, the limit here states that what is the limit of 1 over x as x approaches to 0? When x, this one, x, your x variable, approaches to 0, what happens to your y? It tends to, what happens to your f of x? It tends to go through, or it tends to approach to a relatively large number, which is, in calculus, we define that concept as infinity. Okay? So, the limit of 1 over x as x approaches to 0 is equal to infinity. Or by general rule, when a certain number in calculus, when a certain number is divided by a relatively low number, a relatively large number, for example, a over a relatively low number, that such that it approaches to 0, you will denote that one as an infinity, or a concept that a number divided by a relatively low number that is a relatively large number. The same with infinity, when a divided by a relatively large number, that will yield to a relatively low number, relatively small number, such that it approaches 0. So you must take note of this concept in calculus. Okay? Now, let's go to number 3. This one, limit of square root of x minus 5 as x approaches to 2. We'll try to solve this example. Limit of x minus 5 as x approaches to 2. Okay, so when x the same as usual of what we did with the previous two examples. So by direct substitution, limit of square root of x minus 5 as x approaches to 2 is square root of x minus 5 is equal to square root of 2 minus 5, and that is square root of negative 3. And square root of negative 3 is an imaginary number. Therefore, in calculus, an imaginary number is not a real number. Same with algebra. So the limit of square root of x minus 5 as x approaches to 2 does not exist. Great, does not exist. So if you want to again, by curiosity again, if you want to graph that one, I will not go through that process because mas madugay pa ta. So if you want to graph that one, then you will notice that the graph will not really approach 2, no? The graph in its domain will not really approach 2. So wala gid siya maadtuan, wala ma-approach pod ang imong f of x. So the limit of square root of x minus 5 as x approaches to 2 does not exist. Okay? So that is the concept of the limit. So you just have to remember these warning bells. No? The process of evaluating a function f of x at x is equal to c, and the process of computing the limit of the same function at of the same function at the same value are not equal as processes. Although it is true that for most of the functions that we shall use and for most of the values in their domain, this is a special property called continuity that cannot be taken for granted. So to profound further these warning bells, you just have to take note. You have to knot this on your finger. Evaluating a function f of x at x is equal to c means determining the value of f of c that the function takes exactly at that specific value. Example, if you want to evaluate x squared minus 3x plus 3, if you want to evaluate f of 1, meaning you are determining the value of f of 1 that the function exactly takes place at that specific value. So kung imo ni evaluate kato yung value sa imuhang dependent variable imong makuha, while computing the limit means finding what value the function approaches near that value, that is x approaches c. So kung imong evaluate ang limit ani as x approaches 1, dili gid exactly 1 imong makuha, but it is near 1. So the limit of x squared minus 3x plus 3 as x approaches 1 is just equal to your evaluation of the function at x is equal to 1. Okay? Okay, now let us try to have some more example. This one, evaluate the limit of 3 sine x minus 1 all over 2x minus 2. So we will try to evaluate that one. Limit of three sine x minus 1 over 2x minus 2 as x approaches 1. So again by routinary process by direct substitution. The limit of this one would be, you just have to substitute x is equal to 1, 3 sine of 1 minus 1 over 2 times 1 minus 2, and that is equal to 3 sine 0 over 2 minus 2. And we know that 3 sine 0 is 0. Sine 0 is 0 times 3 is 0. So 0 over 0. And this is one form of indeterminate numbers. 0 over 0, we will infinity minus infinity, and other numbers, other concepts, these are called indeterminate technically. They are the limit can be evaluated, but the limit at this stage cannot be evaluated since they are in the indeterminate forms. Later on, we will know how to evaluate these limits using some rules to be applied. Okay, so what about other examples to evaluate? So we know that evaluating this limit is we can get indeterminate forms, but if we try using it graphically, we can have we might be using graphic calculators that are programmable, that are capable of graphing a function or graphing an equation. So if you want to know the limit, using graphical analysis, this is the graph of this function, 3 sine x minus 1 all over 2x minus 2. As x approaches 1, so as x approaches 1, I'll just have to draw this one. Okay. As x approaches 1, the f of x approaches what? It approaches at this approximate value. Nawala. So this approaches at this approximate value. And this one is approximately equal to 1.5. Later on, you will know why is it that it is 1.5. As I've said a while ago, this one can be evaluated, but at this stage, you cannot evaluate that one because that is indeterminate in nature. So if you want to direct substitute it, you will get in the indeterminate form. Indeterminate meaning it cannot be determined. So later, or as you go along through this course, you will know how to evaluate this kind of limits or this kind of problems. But for now, we have to appreciate the essence of graphing, no? Sa graphing makita nimo nga tama 1.5 gid bitaw sa. But of course, graphing is prone to error. Okay, so now next definition. Another definition for the concept of limit: if as x approaches c while remaining smaller than it, x is greater than less than c, I mean f of x approaches in a finite number L, we say that L is the left limit of f of x, and we write limit of f of x as x approaches to c minus is equal to L. There is a minus there. So that is limit of f of x as x approaches to c minus is equal to L. Or pwede po limit of f of x as x approaches to negative c is equal to L. No. Dili siya pwede kay kung negative, it means that at the negative side of the real number, the Cartesian coordinate system. So we will read as limit of f of x as x approaches to c minus, meaning at the left side of the number. So for example, kani 1, 2, this is the graph. Let's say kanimong point of concern, ang imong 1, this is 1, ang mong 1 minus mo ning diri dapit manimong 1 minus animong 1 minus, this is 1 minus this one, and this is your 1 plus. So kani siya nga graph pa dito is 1 plus, and the kani nga graph is 1 minus. So I hope you understand that two-sided limits. Okay, so next, if as x approaches c while remaining larger than it, x is greater than c, f of x approaches a finite number L, we say that L is the right limit of f of x, and we write limit of f of x as x approaches to c positive is equal to L. So that is the graph, no? Kani mo ni ang c negative, and this one is the c positive. So mo ni mo point of concern nga c. Okay, each of these limits is called a one-sided limit, while a usual limit in which we expect x to approach c from both sides is called a two-sided limit. So we have this technical fact: if both one-sided limits exist and are both equal to the same value L, then the two-sided limit also exists and equals L. If limit of f of x as x approaches c does not exist, then the corresponding one-sided limits may or may not exist. But if they both exist, they cannot be equal. So that is the concept of the limit. To wrap it up, the limit in evaluating the limits of a function, you need to direct substitute the value. Upon substitution, if the number, if you divide a number that is if you divide a number to a relatively low number such that it approaches 0, then your limit is a relatively large number, that is infinity. And if you divide a number to a relatively large number, the limit of that would approach to a relatively smaller number such that it approaches 0. If you get a limit that is not real, that's imaginary, that you consider that a limit does not exist. And also, if you encounter in indeterminate forms, you can use the graphical form, but later you may use some sort of a rule that will help you evaluate the limit. Now let's go to graphical and numerical methods to estimate limits. You just have to go through the definition of this method. Excuse me. I will not recommend using these methods because these are very prone to errors, and as these are only estimations. So the definition: the graphical method of estimating a limit consists of using a graphing calculator or computer program to observe visually the behavior of the function near the given value, and thus making an estimate of the limit value if it exists. So as I've said kanina, no, kani nga kuan kani. So if you want to evaluate the limit using graph, if you know this is the graph of this one, kung maayo nga pagka-graph, makuha nimo nga imong limit ani is 1.5 yun. Pero kung dili pa ay pagka-graph, dili parehas ang interval, dili parehas ang unit na gigamit, then probably you may encounter some issues on the precision of the number that, or the precision of the values that you will get. Okay. Take note that graphical method, while useful, the graphical method provides only an estimate, and sometimes it may provide incorrect solutions. Same with numerical method, it is a method of estimating a limit that consists of constructing a table of values for the function and for values of x closer and closer to c. The pattern of y values obtained can be used to generate an estimate for the limit. The margin of error for this is close to approximately 10% of the total limit for a function. While useful, this numerical method also provides only an estimate and sometimes an incorrect conclusion. Okay, so these are the properties of limits. So please take note of these properties of limits, technical facts. The limit laws: if a limit of f of x is equal to a as x approaches c, and limit of g of x is equal to b as x approaches c with both a and b real numbers, then first you have this limit of f of x plus g of x. You can this in algebra, I think this is a distributive property. You can distribute the limit. So limit of f of x as x approaches to c. So you distribute it into two parts, plus limit of g of x as x approaches to c. So this one kani is a, and this one is b. So if you evaluated this one already, then you just simply add a and b. Same with the operator minus. So if you have limit of f of x, instead of positive here, may mo siyang minus, so kanipod may mong minus. And of course, this one may mo po siyang minus. Okay? Now, what if for the multiplication operator? So limit of f of x times g of x as x approaches to c is just equal to the limit of f of x as x approaches to c multiplied to the limit of g of x as x approaches to c. Or if this again is a and this is b, you just simply multiply a and b, or the limits of these functions. Next, the division. Limit of f of x all over g of x as x approaches c is just equal to the limit of f of x as x approaches to c all over a limit of g of x as x approaches to c. And that is equal to, as again as we defined above, you have a limit of f of x approaches to c, limit of f of x as x approaches to c is equal to a, then and limit of g of x as x approaches to c is equal to b. Then this one you can divide that directly a over b, as long as b is not equal to 0. This time, because this is in algebra form, take note that this is not in a limit form. Kanay dili ni in a limit form, that's in algebra form. If you get an undefined value, then the limit of this one does not exist. Okay? This is an algebra value. Pero kung dito ka nakakuha sa limit mismo, nakakuha kag undefined, that would be infinity. I hope that I am clear with that. Next, limit of f of x raised to g of x as x approaches to c. Then, limit of f of x raised to limit of g of x as x approaches to c is equal to a raised to b. As long again as a and b are not both 0. So if a and b are both 0, these are one of the indeterminate forms in calculus. So these are just the properties of limits. Now, taking cue of the properties of limits, we will evaluate now this function, limit of x minus 1 raised to 2x all over cosine pi x as x approaches to 1. We have many methods to kill a cat, right? So the same with solving this problem, we have many methods. The first one is the conventional one. By direct substitution, you substitute the value of your x is equal to 1. So that would be the limit of or by direct substitution, the limit of this one would be 1 minus 1 quantity 2 raised to all over cosine pi times 1. Okay, so this is equal to 0 over 0. Cosine pi die. 0 times 0 raised to 2 over cosine pi, that is equal to negative 1. And this is equal to 0. Therefore, the limit of x minus 1 raised to 2x over cosine pi x as x approaches to 1 is equal to 0. That is your final answer. Okay, next, definition again for the properties of limits. If f of x can become arbitrarily large as x approaches c, we say that the function approaches infinity, or that its limit at c is infinite, and write, okay, this is the notation to be used. Limit of f of x as x approaches to c is equal to infinity if the values of f of x become ever larger and positive as x approaches to c. So what we did kanina, no, kaninga example. So if the values of f of x become ever larger, so if f of x nato diri is ever larger na siya as x approaches to 0, then the limit of f of x is equal to infinity. Okay, so limit of f of x is equal to negative infinity as x approaches to c if the values of f of x become ever larger and negative as x approaches to c. So the same applies to one-sided limits. So you have to take note of these warning signs. From the technical point of view, if a limit is infinite, it does not exist. The notation limit of f of x as x approaches to c is equal to positive, negative, infinity is meant to provide useful information about the behavior of the function, not to assert the existence of a limit. So meaning wala gyud unta na siya limit kay wala ta kabalo kung unsa jud iyahang exact nga value nga iyahang adtuan. But it is to assert it is to inform us the behavior of the limit. So for example, kana nga graph, it will inform us that the behavior of the limit goes to a relatively large value of f of x. So meaning it is on the infinity side. So the infinity there means that the graph or the function goes to a relatively large value. Okay, so technical fact, we have this limit of law of gravity. If limit of f of x is equal to h as x approaches to c, and limit of g of x as x approaches to c is equal to negative infinity, then limit of f of x all over g of x as x approaches to c is equal to 0. This is what I've said a while ago, no, that if you divide a number, let's say h, this one h, you divide h to a relatively large number and you get the limit, that will yield to a relatively small number. We have also this squeeze theorem. Assume that C is a set of A of B, meaning that A is less than C and is less than B, and that f sub 1 of x is lesser than or equal to g of x and lesser than or equal to f sub 2 of x for every x as an element of A and B, except possibly for x is equal to C. If limit of f sub 1 of x as x approaches to C is equal to L, and the limit of f sub 2 of x as x approaches to C is equal to L, then the limit of g of x as x approaches to C is equal to L. Okay, so we will have to answer these 3 examples before we'll go to vertical asymptotes. So first, we'll answer first problem number 1. What is the limit of 3x all over square root of 1 minus 4x as x approaches to 1/2? Okay, so this is some sort of an exercise. The limit of 3x all over square root of 1 minus 4x as x approaches to 1/2. So by direct substitution again, so you substitute 3, that will be equal to 3 times 1/2 over square root of 1 minus square root 4 times 1/2. Okay, and this is equal to 3/2 over square root of 1 minus 2, that is negative 1. Since we have an imaginary number here, negative 1, square root of negative 1 will yield to an imaginary number. Therefore, the limit of 3x over square root of 1 minus 4x as x approaches to 1/2 does not exist by the virtue of this value. Okay, what about number 2? Limit of sine x all over ln x as x approaches to 1 minus. So limit of sine x all over ln of x. So limit of sine x all over ln of x as x approaches to 1 minus. Okay, by direct substitution, ang anong BDE no? Karon pa ko kabantay. Data by BDS. So by direct substitution, BD. By direct substitution, sine 1 all over ln 1, and that is equal to sine 1 is a number and ln1 is 0. So a number sine 1 over ln over 0 is equal to, since this is at the negative side, this one will yield, repeat what we have learned a while ago, that any number to get any number divided by a relatively small number 0, that will yield to a very large number. So that is an infinity, or a relatively large number. But it is a negative infinity. Why? Because we are getting it at the negative side of 1. So therefore the limit of sine x over ln of x, or the natural logarithm of x, as x approaches to negative 1, as x approaches to 1 minus, is equal to negative infinity. Okay, so those are the properties of limits, and how can you solve that one? How will you evaluate the limits? I forgot, no, atong example ganina. Kani wala na to nagamit ang limits, no, and the properties of limits. I just have to transfer this one. Okay, so we will now use the properties of limits if we can still get 0. So limit of x minus 1 raised to 2x over cosine pi x as x approaches to 1. Now we can use the distributive law, or what we call for that, the distributive property. So kani pwede no kanata exponent nga 2x. You just have to divide this into two limits, the first and the lower limit. So let us define, let a is equal to limit of x minus 1 as x approaches to 1. Okay, let b is equal to the limit of 2x as x approaches to 1, and c is equal to the limit of cosine pi x as x approaches to 1. Okay, so by law, no, properties of limits, this would be limit of x minus 1 as x approaches to 1 raised to limit of 2x as x approaches to 1 over limit of cosine pi x as x approaches to 1. And of course, if you will simplify this one, this will be, so I'll have to clear this one. So this one is kane is equal to A, kane is equal to B, ang kane, this is equal to C. So therefore, that is equal to ito, A raised to B over C. So A raised to B over C. But we know that here, limit of x minus 1 as x approaches to 1 is equal to 0. If you just substitute x is equal to 1, that would be 0. 1 minus 1 is 0. Limit of 2x as x approaches to 1, limit 2 times 1, that is 2. So your B is 2. Of course, we know that this does not violate our rule that both A and B should not be equal to 0. So this is not one of the indeterminate form. Okay, so our C is a limit of cosine pi x as x approaches to 1. We know that pi times 1 is pi, so cosine pi is negative 1. So C is negative 1. And that is equal to 0. So therefore, by utilizing the properties of limits, we know that limit of, therefore, limit of x minus 1 raised to 2x over cosine pi x as x approaches to 1 is also equal to 0. So walang pinagkaiba ang sagot natin using properties of limits and the conventional one. So depende na sa inyo kung sa inyong hiyang. If you want to use the properties of limits, then you may do so. You may also use the conventional evaluation of the limit. Okay? Okay, so let's go now to vertical asymptotes. We have this definition. If a one-sided limit f of x as x approaches to c minus is equal to infinity, or if the limit of f of x as x approaches to c positive or c plus is equal to negative infinity, then f of x has a right vertical asymptote at x is equal to c. Now, for example, this graph, this is the function. No, kani nga graph mo ang function mo. Then, if this function at x as x approaches to c minus, it has a limit of infinity. When x approaches to c minus, then it has a right vertical asymptote. Or if the limit of that function as x approaches to c minus, that is c minus, I think, that is equal to negative infinity. I would like to correct my previous statement, no? The limit of f of x as x approaches to c minus, all of them approaches to x c minus, not the other one, not c plus. So both c minus to be positive or negative infinity of their limit, then they have a right vertical asymptote. Conversely, we have also if limit of f of x as x approaches to c positive or c plus, they are equal to positive negative infinity, then f of x has a left vertical asymptote at x is equal to c. So as you can see in the graph, the asymptote is on the left of the function or left of the graph of the equation. So we have these warning bells for vertical asymptote. The line x is equal to c may be both a left and right vertical asymptote, and it may be so with different types of infinities in either side. So we have the first graph. This one, it is exactly the mirror of this graph. So this one is exactly the mirror of this, but this one is not quite the mirror of the other one. So they have different infinities on the other side. So though they have the same infinities at this portion at the asymptote, but on the other side they have different infinities. Alpita, just to be clear, this one, this kaning graph, kaning ha, though they have the same infinities on this side, at this side they have different infinities. The same here, though they have the same infinities, this one they have different infinities on this side. It is on positive infinity, and this one a negative infinity on this side. This side is positive infinity. However, on this side also they have different continuities. So you have to be careful on determining their infinities on both sides. Strategy. This one. This is the what you are waiting for on how to discover vertical asymptotes. Vertical asymptotes occur mostly in one of these situations. When the function includes a fraction whose denominator becomes 0 for some value of x, and when the function includes a transcendental portion that is known to have a vertical asymptote. What are transcendental functions or transcendental functions? Just like ln, the natural logarithm, the logarithm, they are considered to be transcendental functions. However, in both cases, the existence of the vertical asymptote must be checked by computing the relevant limit, since other graphical features may also correspond to such situations. Okay, let's have this example. Find the vertical asymptote of y is equal to 1 all over square root of 4 minus x squared. So y is equal to 1 over square root of 4 minus x squared. We know, we have mentioned a while ago already, that the strategy for discovering vertical asymptote is to check whether the function involves a fraction, and if it is involving fraction, you get the denominator, equate it to 0, then find the value of x that will somehow put the entire function into somehow put the denominator that will equate the denominator to 0. So square root of 4x squared is equal to 0 according to the strategy that we have. So this one, you square both sides so that you may omit the radical sign. So this one would be 4 minus x squared is equal to 0. Transpose 4 to the right. Negative x squared is equal to negative 4. X squared is equal to 4. You multiply this one, both parts of the equation, by negative 1. Then extract both sides of the equation. This would be x would be now equal to, we have two roots, positive and negative 2. Okay, so we have now values of x that will equate this one to 0. These are the possibilities of your uh, vertical asymptote. Now, according to what we have learned a while ago, uh, this definition would test whether these values would satisfy the vertical asymptote of this function. So we need to compute the limit of the limit of 1 over square root of 4 minus x squared as x approaches to 2 and negative 2, so that we may know whether these values x is equal to positive or negative 2 is a vertical asymptote to this function. So to test whether x is equal to 2, so for x is equal to 2, limit of 1 over square root of 4 minus x squared as x approaches to 2 okay, and that is equal to, so by direct substitution again, you will get what? 1 over square root of 4 minus 2 squared, that is 4, and that would be equal to 1 over 0. According to calculus, this is infinity. So therefore, x is equal to 2 is what? A vertical asymptote to function y is equal to 1 over square root of 4 minus x squared. Okay, now what about the negative 2? So 4x is equal to negative 2. We again get the limit of 1 over square root of 4 minus x squared as x approaches to negative 2. Then by direct substitution, this one would be, by direct substitution, 1 over square root of 4 minus negative 2 squared is still 4, and that is equal to 1 over 0, or in a calculus this is considered to be infinity. So therefore we conclude that x is equal to is also a vertical asymptote to function y is equal to 1 over square root of 4 minus x. Okay. So we have two asymptotes, x is equal to 2 and x is equal to negative 2. Okay, what about the number 2? You need to get the vertical asymptote of y is equal to x cubed all over x minus 1. X cubed all over x minus 1. So the same process that we have to go through. Number 2, y is equal to x cubed all over x minus 1. You make use of your denominator equal to 0 because this is a fraction. So x minus 1 is equal to 0. Then x is equal to 1. So this is one possibility that this is a vertical asymptote. How to check whether this is a vertical asymptote? You need to check on its limit. Dapat ang limit ani as x approaches to 1 must approach infinity. So limit of x cubed over x minus 1 as x approaches to 1. So by direct substitution again, routinary process, 1 cubed over 1 minus 1, and that is equal to 1 over 0, or in calculus this is infinity. So therefore excuse me. Therefore x is equal to 1. Therefore, di na mo agi. Therefore, x is equal to 1. Therefore, x is equal to 1 is a vertical asymptote of y is equal to x cubed over x minus 1. I hope things are clear already, no, for vertical asymptotes. We have now the horizontal asymptotes. Definition: we say that a quantity q approaches infinity and write q approaches to infinity as in a notation when q can be made larger than any predetermined positive value. We say that a quantity q approaches negative infinity and write q approaches to negative infinity, so that is the notation when q can be made less than any predetermined negative value. So as we mentioned already a while ago, that symbols positive and negative infinity are representing only concepts. They do not represent numbers. So therefore, usual algebraic rules do not apply to them. So just like infinity minus infinity, that does not apply to them because they are just concept. So they are in if we encountered infinity minus infinity, then that would be one form of indeterminate forms. Okay, another definition: a limit of the form limit of f of x as x approaches to positive or negative infinity is equal to c is called a limit at infinity. A limit of the form limit of f of x as x approaches to positive and negative infinity that is equal to positive or negative infinity, that is called a limit or infinite limit at infinity. So if you get a number, a real number of a function whose limit is that its x approaches to positive or negative infinity, then that is called a limit of infinity or limit at infinity. If you take the limit of a function as x approaches to positive or negative infinity and you get a concept again of positive and negative infinity, then you call that one as infinite limit of or infinite limit at infinity. So these are just one of the few things to remember. If limit of f of x as x approaches to positive or negative infinity is equal to positive or negative infinity, the graph exits towards the corner of the window as shown in the picture. So if this one is limit of f of x as x approaches to negative infinity equals infinity, then the graph exits toward here. Same for this function, same for this evaluation of limits, the graph towards here, here, and here. You just have to familiarize this graph. Limits at infinity, be they be finite or infinite, make sense only if the domain of the function extends to the appropriate type of infinity. Otherwise, they do not exist. An infinite limit at infinity does not exist as a limit. Its notation and terminology are meant to provide additional information about why the limit does not exist rather than state its existence. So basically, theoretically, 1 over 0 is the limit there, it does not exist. I just have to define that the limit there, the behavior of your graph extends to a relatively large number such that it approaches infinity. Another one, an infinite limit at infinity only tells us the general direction in which the graph exits the window. So what I have shown already a while ago, not how fast it does so or with what patterns. More calculus methods are needed to obtain such information. So as you go through the calculus, differential and integral calculus, you will know the how fast and how to optimize these graphs. Now, to take the limit, for horizontal asymptotes, these are the definition. If a limit of f of x as x approaches to infinity is equal to a, where a is a finite number, the line y is equal to a is called the right horizontal asymptote for the function f of x. Or, if the limit of f of x as x approaches to negative infinity is equal to a, where a is a finite number, the line y is equal to a is called the left horizontal asymptote for the function f of x. Okay, excuse me. Okay. If a function is of the form f of x is equal to p of x all over q of x, where as x approaches to infinity, p of x is bounded and limit of q of x as x approaches to infinity is equal to positive or negative infinity, then limit of f of x as x approaches to infinity is equal to 0 and y is equal to 0 is a right horizontal asymptote for the function. The same occurs as x approaches to negative infinity for left horizontal asymptotes. You just have to grasp the meaning of this technical fact, and then you will definitely know how to get the horizontal asymptote of a specific function. So just like the vertical asymptote, there is also a strategy for limits at infinity. You have the law of jungle. To compute limit of p of x as x approaches to positive or negative infinity of q of x all over q of x, it may be effective to divide both p of x and q of x by a term that is largest as x approaches to positive or negative infinity among those used in the function and then computing the result. Warning bells. The expression largest term is very vague and it can be interpreted easily when dealing with powers or polynomials or just exponentials. It can become very dangerous when dealing with more complicated mixtures of terms and factors. So we don't have example for horizontal limits. I will have one later. I'll just have to go through first continuities and discontinuities. Continuities. A function y is equal to f of x is continuous at a value x is equal to c if its graph has no breaks of any kind at that value. A function y is equal to f of x is discontinuous or has a discontinuity at x is equal to c if its graph has some type of break at that value. A function is continuous if it has no discontinuities between any two values at which it is continuous. I'll repeat between any two values. If it has no discontinuities between any two the values, then that is considered to be continuous. Now, a function y is equal to f of x is said to be continuous at a value x is equal to c if the limit of f of x as x approaches to c is equal to the evaluation of the function f of c. This requirement is equivalent to the following three conditions taken together. If f of c exists, that is, c is in the domain of f of x, and the limit of f of x as x approaches to c exists as a unique finite number, the two above values are equal. Okay? So you need to get or evaluate first f of c, and if it exists, okay, check so number 1. Next, get the limit of f of x as x approaches to c, and if it exists, it is a unique finite number, then check. You need to compare the result of your 1 and 2. If they are equal, then check. If these three conditions are satisfied, then your function is said to be continuous at a value x is equal to c. If one of the above three conditions is false, then the function is said to be discontinuous at x is equal to c. A function y is equal to f of x is left continuous at x is equal to c if the limit at x is equal the limit of f of x, as x approaches to c minus is equal to f of c. A function also y is equal to f of x is right continuous at x is equal to c if the limit of f of x as x approaches to c plus is equal to f of c. We have this IVT, or the intermediate value theorem. If f of x is continuous in a closed interval, so we have discussed this partially on the domain of functions. So closed interval meaning bracket AB, meaning if x is an element of a and b, meaning a is lesser than or equal to x, such that x also is lesser than or equal to b, and the function f of a is lesser than or equal to k, and k is lesser than or equal to f of b, then there is at least one value c, such that a is lesser than or equal to c, and c is lesser than or equal to b, and f of c is equal to k. So in more concrete terms, as we trace the graph of such functions starting at a, f of a, and going all the way to b, f of b, we shall find at least one point whose coordinate is between f of a and f of b. Strategy for identifying and classifying discontinuities. First, identify the values for which something unusual occurs in the formula or definition of the function. So you may check on the function whether it is if it is a fraction, then something unusual occurs at the denominator when it becomes 0. When it is a radical function that involves roots, then something happens when it becomes imaginary. Something unusual occurs when the function becomes imaginary. When it involves transcendental functions, there are existing properties for transcendental functions. For example, logarithmic functions. We know that logarithmic functions are only real up to values of 1. Below than 1, below 0, that would yield a undefined value or not real values. Second, evaluate the function at each such value. Then third, compute the left and right limits of the function at each such value. Fourth, if the function and the limits all exist and are equal, conclude that the function is continuous there. If the equality limit of f of x as x approaches to c is equal to f of c does not hold, classify it by using the information so collected. A single point hole occurs. Okay, we have here the single point. This is one part of the discontinuity. A single point hole occurs when limit of f of x as x approaches to c exists and f of c does not exist. So it happens. So later we will find some examples that will prove this definition. This means that the function is approaching a finite value but does not reach it. The resulting hole is usually represented by a small hollow circle. Single point holes and displaced points are also called removable discontinuities, since the function can be made continuous at those values by changing a single function value and defining f of c is equal to limit of f of x as x approaches to c. A vertical asymptote occurs, as we know already during our discussion in the vertical asymptote, when limit of f of x as x approaches to c minus is equal to negative, positive, infinity, or limit of f of x as x approaches to c plus equals negative or positive infinity. Now, another definition that would help you in the domain, finding the domain of the function. An end of domain discontinuity occurs when f of x is not defined in an interval to the left or to the right of that value. We have also here the jump occurs when limit of f of x as x approaches to c minus and limit of f of x as x approaches to c plus both exist but are not equal. So this graph, this one is called piecewise function. So we have here the limit of f of x as x approaches to c minus, and we have the limit of f of x as x approaches to c plus. In that case, the graph is approaching two different finite values, one from either side. Okay, so we will now take examples for vertical, horizontal asymptotes and continuities and discontinuities. Okay, so we'll have these examples. Again, we have already computed, we have already solved these two examples a while ago for the vertical asymptote. So we'll add two more. Find the vertical asymptote of y is equal to square root of x plus 3 all over x squared minus 25. So our goal here is to make this function into an infinite limit so that we may find the vertical asymptote. So as what we have learned a while ago already, that we need to set, if the fraction is involving if a function is involving a fraction, we need to set the denominator to 0, such that for this example y is equal to x cubed, x plus 3, sorry, x plus 3 all over x squared minus 25. To set this one to an we will set this one into that denominator. We will equate this one to 0. So x squared minus 25 to make this whole function, to make this whole function as we evaluate the limit, to make that whole function infinite. So the limit is at infinity. So you should equate this one to 0. So x squared minus 25 is equal to 0. So x squared is equal to 25. Extracting the roots, we have two roots for x, that would be positive and negative 5. So you have now positive and negative 5. We need to test whether positive or negative 5 is really the vertical asymptote of this function. So limit of square root of x plus 3 over x squared minus 25 as x. First, we need to test as x approaches to 5, positive 5. So by direct substitution, I'll just have to delete this one. So by direct substitution, your 5 square root of 5 plus 3 all over 5 squared is 25 minus 25, and that is equal to square root of 8 all over 0. By the rule of according to what we have learned already, any number divided by a relatively small number such that it is close to 0, that would be equal to infinity. So therefore, because the limit of square root of x plus 3 all over x squared minus 5 as x approaches to 5 is equal to infinity, then therefore we can conclude that x is equal to 5 is a vertical asymptote of the function. Okay, what about negative 5? So for x is equal to negative 5, we need to test again the limit of square root of x plus 3 all over ano sa itong isa? X squared minus 25. This time as x approaches to negative 5. If the limit of this is still positive or negative infinity, then we could say that this function x is equal to negative 5 is a vertical asymptote. Otherwise, if it is not, then x is equal to negative 5 is not a vertical asymptote. So therefore, x is equal to negative 5, or by direct substitution, you have here square root of negative 5 plus 3 over negative 5 squared, that is 25 minus 25, and this is equal to square root of negative 2 over 0. And take note, square root of negative 2 is an imaginary number. So therefore, the limit of this one is, the limit of square root of x plus 3 all over x squared minus 25 as x approaches to negative 5 does not exist. And therefore, x is equal to negative 5 is not what? Is not a vertical asymptote, since the limit is not equal to infinity or negative infinity. Okay? So we just have to go back to the definition of vertical asymptote. According here, this one, According here, may asymptote ka lang if the limit equals to infinity. Whether it be positive or negative infinity. So, with this example, hindi naging infinity yung limit natin. So, therefore, x is equal to negative 5 is not a vertical asymptote. So, we can conclude now that for this problem, y is equal to square root of x plus 3 all over x squared minus 25. The only vertical asymptote is x is equal to 5. Now, what about number 2? Find the vertical asymptote of y is equal to x all over e raised to x minus 1. Okay, so we will solve again. Y is equal to x over e raised to x minus 1. Again, the function involves the function is a fraction. So we will equate the denominator to 0. So e raised to x minus 1 is equal to 0. So e raised to x is equal to 1. Okay. So according to the law of exponents and taking the logarithm, natural logarithm of both sides, we have ln of e raised to x is equal to ln of 1. Ln of e raised to x is a property of logarithm, that would be x, and that is equal to 0. So this whole function will become 0 if x is equal to 0. Now, x is equal to 0 is a candidate function that this equation will become that this equation has a vertical asymptote. But we must check first whether the limit of this function as x approaches to 0 is equal to infinity. If it is equal to infinity, then x is equal to 0 is a vertical asymptote. Otherwise, if it is not infinity, then x is equal to 0 is not a vertical asymptote. It does not have any vertical asymptote. So we will check the limit of x over e raised to x minus 1 as x approaches to 0, because we get 0. That must be equal to infinity, so that x is equal to 0 hold true as a vertical asymptote. So, by direct substitution, 0 over e raised to 0 minus 1 is equal to 0 over 1 minus 1, and that is 0 over 0. 0 over 0 is an indeterminate form. It cannot be hold true as an infinity. It is an indeterminate form. So, because it is not equal to infinity, therefore, x is equal to 0. Please ang 0 over 0 is not equal to 0. Diri lang kataman sa 0 over 0. Dara kataman yung solution. Pag mo ibutang pag mo nag equal to 0, mamali na ka. So, therefore, x is equal to 0 is not a vertical asymptote. Since x is equal to 0 lang man imong possible candidate, dili man siya vertical asymptote. Therefore, this function y is equal to x all over x e raised to x minus 1 has no vertical asymptote. So, for number 2, no vertical asymptote. Now, let's go to horizontal asymptote. Find the horizontal asymptote of y is equal to x cubed minus 8x plus 12 all over 4x minus 3x squared plus 5x cubed. This time, the rule of the technique in finding the horizontal asymptote of a function is that you get the limit of the function and it should approach to infinity. Okay, let's try this one. Y is equal to x cubed minus 8x plus 12 all over 4x minus 3x squared plus 5x cubed. So, you get the limit of this. Limit of x cubed minus 8x plus 12 all over 4x minus 3x squared plus 5x cubed as x approaches to, this time, infinity. So, you need to evaluate the limit as x approaches to infinity. And if a limit if after evaluating the limit it has a value, a real number, then that real number is the horizontal asymptote. Therefore, the limit of this one as x approaches to infinity is the horizontal asymptote. So, by direct substitution, in evaluating the limit of a function as x approaches to infinity, we will use the laws that we defined already a while ago. The law of jungle, this one. So, to compute limit of p of x all over q of x as x approaches to infinity, it is effective to divide p of x and q of x by a term that is largest. So, for this particular example, the term that is largest is x cubed. Please take note and let this serve as a warning bell. This strategy is only true if it does not involve transcendental functions or other functions other than algebraic functions. So, dapat kung maggamit ka law of jungle, dito lang ka magamit sa algebraic functions. This is the warning bell here. It can become very dangerous when dealing with more complicated mixtures of terms and factors. So I hope this is very clear that the functions involved on your limit is homogeneous, meaning walay sagol, kani dapat purely algebraic functions. Okay, so limit of x cubed minus 8x plus 12 all over 4x minus 3x squared plus 5x cubed as x approaches to infinity. So, we divide both. We divide all the numerator and the denominator, all terms of the numerator and denominator by the largest, the term that is the largest. So, this is equal to, I just have to divide it on the other whiteboard because it is not, the board is quite small. So it will look like this: x cubed minus 8x plus 12. Since our the greatest term is x cubed, so we divide it by x cubed. I repeat, don't divide it with the term that is largest including the coefficient. Dili nimo i-divide apil ang coefficient kadto lang term niya, katong iyang variable, largest term of the function. So you divide it now, i-divide na lang nako daan. So you divide it by x cubed all over 4x minus 3x squared plus 5x cubed. Again, divide it by x cubed, and x cubed. Okay? So, in algebra, kani mahimo ni siyang 1. Kani pod mahimong 5 na lang ang mabilin. Kani mahimong makancel ni, mahimo ni siyang 2. Okay? Squared ay. And then the same here kani makancel ni, kani mahimo lang x. Kani mahimong x squared times f. So therefore, the final function would be, after dividing the largest term, a term that is largest, would be 1, x cubed over x cubed is 1, minus 8 over x squared plus 12x cubed, all over 4 over x squared minus 3 over x plus 5. So we need to get the limit of that one as x approaches to infinity. So by direct substitution, we substitute now infinity to x's. Then by direct substitution, and according to the rule, the law of balloons, no, if a number is divided by a very large number, you will get a smaller number. So if you divide 8 over x squared by a relatively large value, then you will get here, you will yield here a result of a relatively smaller value such that it is close to 0. So basically, kung ay imuhang value 8 over x squared kani over x cubed kani o kani, this or all become 0. Okay, divide man ani mo infinity, and infinity by concept is a relatively large number. So ang mabili na lang nimo nga mga values is a constant value 1 for the numerator and a constant value 5 for the denominator. Therefore, the limit of that function as x approaches to infinity is equal to 1/5. So therefore, for this function, we know that this is 1/5. Therefore, y is equal to 1/5 is the horizontal asymptote. Okay? Y is equal to 1/5 is the horizontal asymptote. I hope that this is clear to you, so that we may now proceed to the next example. Okay, find the horizontal asymptote of this function. Okay. Find the horizontal asymptote of this function. Square root of 3x squared minus 5x plus 6 all over 2x minus 4. Number 2. So, number 2. We will now find the horizontal asymptote of square root of 3x squared minus 5x plus 6 all over 2x minus 4. So that is equal to, okay, so to find the horizontal asymptote, again, the rule is to evaluate the limit of the function as x approaches to infinity. So whatever result it may yield, that will be, if it is a real number, then that is the horizontal asymptote. So here, limit of square root of 3x squared minus 5x plus 6 all over 2x minus 4 as x approaches to infinity, that is equal to, so now the law of jungle cannot be applied here because this is not homogeneous. You have a radical function at the numerator
and a linear function at the denominator. So radical function is very tedious to evaluate, and you cannot have a largest term here because of this radical function, no? So you just leave it that way, then we'll have to evaluate pwede dahil nga inyong i-divide og x squared both parts of the equation. Pwede nga mahimo siyang x over 4. You divide both parts both terms by x over 4. Okay. So square root of 3x squared minus 5x plus 6 all over 2x minus 4. Okay, so you divide it by what is the largest term here, that is x squared, but because of the radical you need to square it, so that would be x to the 4th. So you divide it by square root of 3x squared minus 5x plus 6 over x squared lang pala, x squared. But here ang imong i-divide sa ubos dili na x squared but only x. So 2x minus 4 over x na lang, so that walay ma-alter sa imong equation. This is equal now to square root of 3 minus 5 over x plus 6 all over, this one is 2 minus 4 over x. But take note also that the x here comes from what? Kani nga x comes from the square root of x squared. And we know that square root of x squared is a positive or negative, has a positive or negative values. So you should take note that this will be positive and negative x. So whatever result we may have here, that it always have two results, the positive result and the negative result. So therefore this one is 3, square root of 3 minus 5 over x plus 6 over x squared. I'm sorry, this is 6 over x squared all over 2 minus 4 over x. Then taking the limit by direct substitution, so limit of square root of 3x squared minus 5x plus 6 all over 2x minus 4 as x approaches to infinity is equal to the limit of square root of 3 minus 5 over x plus 6 over x squared all over 2 positive negative 2 minus 4 over x as x approaches to infinity. So if x approaches to infinity, this is 0 and this is 0 and this is 0. Therefore the values that we have will be positive, negative, square root of 3 over 2. So we have two horizontal asymptotes. Therefore y is equal to positive, negative, square root of 3 over 2 are our horizontal asymptotes. Okay, so I hope that that is clear to you already. Okay, so I guess that is all for the limits and continuities part 1. The continuities and discontinuities, the examples of such will be thoroughly discussed on the limits and continuities part 2. And the third example for the horizontal asymptotes will be for your own consumption. So these are the references we have from the Love and Rainville, and the Prater and Prater, and also the Roberto Math notes that I have used. The modular lectures that I have uploaded comes from that site, Roberto's Math Notes.com. It was retrieved last August. So any questions? If you have questions to be addressed, please don't hesitate to contact me through WhatsApp application. Next video to be uploaded will be the limits and continuities part 2. So thank you so much for listening to this video.